Hello everybody. Today we're going to talk a little bit about how we geotechnical engineers can estimate and actually predict induced stresses or stresses from loads that we place on the soil, and particularly focusing on two types of loads. Loads that we're going to assume are infinitely small points, and loads that we are going to assume are lines. Uh, as a recap or as a review, we've talked a little bit about if I have the ground surface and I have some soil element down in the ground, that soil element is going to be feeling stresses. And those stresses we typically say are the geostatic stresses, or the stresses from the weight of all this overburdened soil that is on top of the soil, or on top of our soil element. We may even have some shear stresses if we have an embankment up here, and though that embankment is applying some sort of shear demand on our soil. And so if that's the case, we may have shear. But what I want to talk about today is, let me get a new drawing here. What I want to talk about today is how do we estimate stresses? Namely, if I put some new load on the ground surface, what is that going to do to increase the stresses that my soil element feels? And again, why do I care about this? Well, I care about it because if I zoom in on my soil element and I add a stress to it, it's going to cause it to want to shrink and to expand in the horizontal direction. If that's what it looked like before, it wants to go out and it wants to contract and shrink. These deformations can cause problems if we have structures built on top of it. Even worse than that, however, would be if I have my soil element and those stresses get to be so big that the soil itself fails in shear, and the soil is not capable of holding those stresses that I'm applying to it. So those are things that we need to be cognizant of when we talk about induced stresses on the soil. Now, I want to talk about specifically three methods that geotechnical engineers commonly use for estimating stresses. The first method is called the simplified 2-to-1 method. This basically is what I might call the back of the envelope type of calculation, or it's a very crude method to distribute some sort of load down through the soil at a slope of 1 horizontal to 2 vertical. So all we're assuming is that the soil particles are distributing these loads out, so that the deeper we go, the broader that cross-sectional area becomes that load is distributed over. Now this approach is super easy. All we're going to do is use this equation right here, where we say that the change in the vertical stress is equal to the induced load on the ground surface divided by this area of the width plus the depth times the length times the depth. So if we use that equation, we can come up with a very crude approach. Now, the method tends to be conservative, meaning that it's going to predict larger stresses than actually exist in the soil, but that's okay. Now here, based on my observations, nobody uses this method in practice. It's just something if you want to really quickly check yourself, it's great. The next method is what I call, or what others also call, elastic methods. These methods are derived from elastic solutions, and there's two different approaches. There's the Boussinesq approach, and there's the Westergaard approach. In this particular class, because this is an elementary soil mechanics class, we are not going to talk about the Westergaard approach. but we will talk about the Boussinesq approach in the next few slides. This method right here is easily the most commonly used method in geotechnical engineering practice today. But coming up behind it is the third method that I just briefly want to talk about, and these are numerical solutions or finite element modeling methods. These approaches are becoming more and more common as they become more and more validated. Software becomes easier and easier to use, but engineers still are going to fall back to elastic methods. In other words, if they run a finite element analysis, they're still going to check it against the elastic methods to make sure it gives them about the same answer anyway. So you're likely not to see this method except on the large projects or the costly projects, but I am going to predict that those methods are going to become more common in the future. Looking at stress-based, stresses calculated using elastic theory, we like this approach for a few reasons. First of all, they tend to give us closed-form solutions. That means that we can get a very simple equation that you can just program into a spreadsheet or like a MATLAB program. And these solutions tend to be conservative for most cases, meaning they're not going to underpredict the stresses usually, though in some cases they can. But the problem with these approaches is that sometimes engineers use these solutions blindly. Not good, meaning that they treat it like a black box. You have to understand when you use these elastic equations that they may not be valid for all scenarios, and you should be aware of the assumptions that you're making when you use these solutions. And what assumptions are these? Well, namely that if I was to plot the stress-strain behavior of the soil, I'm assuming that the soil is sticking to this linear region right here, and it's not going into the plastic region at all. And that may be a valid assumption, but it may not be also. We're assuming linear soil behavior. We're assuming that the soil is elastic, meaning if I load it up, it's going to deform. If I let it go, it's going to rebound back to its initial state or location. We're going to assume that the soil is isotropic, meaning that the elastic modulus in the x and y directions are equal. And we're going to assume that the soil is homogeneous, meaning that no matter where I am in that soil layer, the same properties are going to exist. So now let's look at the, I'm not sure why my pen did that. Let's look at the Boussinesq solutions. Boussinesq was a French engineer, and using elastic methods derived a whole series of equations that would give us stresses or induced stresses in the y, in the x, and in the z direction on a soil element from different types of loads placed on the ground surface. Now, this particular solution I'm showing you is for a point load. So imagine, I'm stealing my thunder. Imagine if I were to take, I don't know, let's see, I'm drawing in 3 dimensions the ground surface. And let's imagine that I place a ballpoint pen right on the ground surface. And then I train, I don't know, a giant elephant named Pinky to stand on this pen. And so Pinky is just a massive elephant. And so Pinky has a lot of weight associated with her. And she's applying all of that weight right at the tip of that pen that then is going to get radiated down in all directions into the soil. That's what we're talking about, and that's what we're assuming with a point load, that there's a massive load, but it's being applied to an infinitesimally small point. Now, I could spend slide after slide after slide deriving the Boussinesq solution for this, but there's plenty of literature out there that will do that for you. What I want to do is give you the solutions. So the solution for this point load equation in the z direction, which tends to be the one we care about the most because it's the vertical direction, is equal to this solution right here. And then if I want it in the x direction, I can use that equation. And if I want it in the y direction, I can use that equation as well. And you'll notice, by the way, that these equations are exactly the same. The only difference is I'm changing my units of y or x. And you'll also note that these equations for x and y are incorporating the Poisson's ratio, which again is an elastic property that describes how much the soil squishes out horizontally when you squish it vertically. So there's some interesting things. I want you to take some time, maybe pause the presentation, and I want you to look at the format of these equations. You'll see that there's a term r for the radius from the point out to directly over where your point of interest is. So remember, radius is the radius along the ground surface. L is like the hypocentral distance, which is just a straight line from the ground surface down to the center of your soil element. And you'll notice Z is the depth from the ground surface down to your soil element of interest. Look at this equation and see if anything seems strange to you. Okay, did you come back? And or welcome back. I hope you took a moment to pause and to think a little bit about what's different and unique about this equation. And I did steal my thunder a little bit before, so maybe you got it right. But what's unusual about these equations is you'll see that there's no modulus of elasticity. In other words, there's no E sub x, and there's no E sub y, and there's no E sub z. And the reason for that is we assumed that the soil is isotropic. And when you assume that, the modulus cancels itself out. What does that mean? That means that no matter what my soil is, whether it's clay, whether it's sand, whether it's gravel, whether it's silt, whether it's organics, whether it's marbles, it doesn't matter. Whatever the soil is, we completely neglect the elastic properties of that soil. And we assume that the properties are going to be the same regardless of the soil type. Did you hear me, folks? Soil type does not matter when we talk about Boussinesq and elastic solutions. So the nice thing about that assumption is that I don't need to know what is actually there to estimate what the stresses or the induced stresses are going to be from some load that I'm applying to the ground surface. So here's some interesting questions. What types of things can we treat as point loads? Well, we can treat any nonlinear load where the depth of our soil element is greater than 3 times the width of our load. So if I put like a square footing on the ground, as long as my depth down is greater than as long as my depth is greater than 3 times my width, I can treat this square footing as a point load, and I'll still be in the ballpark of a feasible solution. What's one of the greatest advantages of this method? Well, one of the things we like about elastic methods is that we can apply the principle of superposition, meaning we can take a complex load, break it up into a whole bunch of individual loads, whatever those may be, compute the response from each one of those loads, and simply add them together. So let me demonstrate for you. Let's imagine that we want to determine the vertical stress. That is going to be delta sigma z, or another way we can write that is delta p sub z. at a depth of 3 feet below the wheel, or below one wheel, due to a 747 airliner assembly. So in other words, this 747 massive airliner is sitting on the runway. If I take that configuration of the wheels and I flip them up and I look at them in plan view, this is what it's going to look like. So we can see that the wheel spacing is 4.83 feet, and in the X direction and in the Y direction, the spacing is 3.67 feet. What I want to do is I want to compute the stresses beneath this wheel right here at a depth of 3 feet below the ground surface. So we can use our point load assumption here, because we can treat each tire as a point load. So we actually have 4 different point loads, and we're going to compute the point load for each of the 4 tires and then just add them together. So here we go. P, by the way, happens to be the weight on any individual tire, which was given to us up here as 44,000 pounds. And other thing we need to define, I think we already did this, X direction is in this way and Y direction is up and down. Okay, so if I want to know the loads beneath tire 1, and I've defined my point beneath tire 1 as the origin, meaning X equals 0, Y equals 0, then all I have to do is plug in my Z's, my X, and my Y's. So my depth Z, as we already discussed, is going to be 3 feet. Because we're at the origin beneath tire number 1, my X value is going to be 0, as will my Y value be 0, because I'm already beneath tire number 1. And then, as we discussed already, Z is 3 feet. So when I compute that, I get 2.33 thousand pounds per square foot, or 2.33 kips per square foot. Now let's do it for tire number 2. So this is going to be this tire right here. This tire is located at a Y value of 3.67, and X is still going to be 0. So Z 3, X 0, Y 3.67, and Z of 3. And that gives me an induced stress of 0.24 kips per square foot. So why don't you pause and see if you can compute the values that I did and plug in the right numbers for X, Y, and Z. Go. Okay, hopefully you're back and you were able to get those numbers. If you weren't able to get them, let's help you out. For tire number 3, tire number 3 is right there. X is going to equal 4.83 feet, because here's my origin and I'm moving to an X value of 4.83. Y is going to equal 3.67 feet, because there's my origin and I'm moving up to a value of 3.67 for tire number 3. And depth is going to remain at a value of 3 feet. So that's how I got my 0.04 kips per square foot. And on the 4th tire, X is going to equal 4.83 feet, and Y is going to equal 0. And that's how I get 0.1 kips per square feet. Okay, so now I have 4 induced stresses from 4 tires on the wheel assembly of the jet. All I need to do now is sum them all together. And when I do that, I get a total predicted induced stress from this wheel assembly beneath tire number 1 at a depth of 3 feet equal to 2.71 kips per square feet. That's why superposition is really, really useful. But what if I don't have a point load? What if I have something that's long and linear? In that particular instance, that we may use Boussinesq solution for a line load. which is essentially just the solution of a point load integrated in a particular direction of the line load. So when we do that solution, what we're doing is we're just saying the line stretches out infinitely in one particular direction. In this case, it's in the y direction. And you can see that the line the load just follows along that line. And what that's going to do is it's going to produce a series of stresses that are going to peak right beneath the center of that line in the y direction. And as you move away from the y, it's going to produce smaller and smaller stresses, as you can see on this stress distribution down here. And so this is, by the way, an assumption that we call plane strain loading. Plane strain loading basically means that in the direction of the loading, or in the axis of the loading, there is no strain. Which means if my little soil element, draw it in 3 dimensions here, wants to strain outwards in the y direction, it can't, because this line just keeps going infinitely in that direction, which means that the soil element next to it along that same line is also trying to strain. And they cancel each other out. So that means that no strain can occur in that line of loading. But strain can occur in the x-axis and in the z-axis. So the solutions then for the line load are given here. The change in stress, or the induced stress in the z direction, the induced stress in the x direction, and interestingly, the induced stress in the y direction. But wait a minute. I thought you said from plane strain that there's no strain in the y direction. Yeah, that's true. There's no strain. But that doesn't mean there's no stress. Stress and strain are related, but they're not the same thing. So we can have a change in stress in the y direction, but just no strain. So what kinds of things can we approximate as a line load? Well, maybe like a long wall, the footing for a long wall, or maybe a long strip footing, as long as the depth of my soil element is greater than 3 times the width of my strip footing. Cool, so that's line loads. I forgot one. I'm sorry. Any rectangular load where the length of my footing is greater than 5 times the width and the depth of my soil element is greater than 3 times the width. Whenever I have a rectangular footing, by the way, it's good for you to get used to the notation. The long side of the rectangle is always going to be denoted as L, and the short side of the rectangle is always going to be denoted as B. Always. So just imagine L means long. So anytime my long side of my rectangle is greater than 5 times the width of my rectangle, then I can apply this line load assumption. Okay, awesome. So that's line loads. But what if I have a load that doesn't meet any of these assumptions here? And it doesn't meet the assumptions of a point load. Well, then we got a problem. Not really, but it just is going to make our solution more complicated, because now we're going to use a Boussinesq solution for what's called a strip load. So the point load integrated in one direction, maybe the y direction, is going to give us the line load. But then if we integrate it from maybe some x equals 1 to x equals n value in the x direction, so we have a double integration going on, this is what's going to give us a strip load. So we're essentially just integrating the line load in some along the x-axis. So it gives us an infinitely long but a finite wide load that we're applying to the ground surface. So strip footings are really handy, and they represent actual footings that we place on the ground surface. The problem is that because now we're double integrating, we have a really complicated solution, which if I solve the solution, I'm going to get this equation for the z direction, this equation for change in my stress in the x direction, and this equation for change in my stress in the y direction. So you can see that it's a lot more complicated. We also have this trigger function lambda, which lambda is going to equal 1 if these conditions hold true. X, by the way, happens to be the distance from beneath the center of my strip load out in the x direction. So in other words, all this is saying that if B is the total width of my footing, and I fall between minus B divided by 2 and B divided by 2, what that basically means is as long as my soil element is located beneath the footprint of my strip load, then lambda is going to equal 1. The second my soil element of interest is outside the footprint of my strip load, then lambda is going to equal 0. That's what that little trigger or qualifier means. And by the way, in using these equations, whenever you have these tangent functions, for instance, please make sure that you have your calculator or spreadsheet set to radians for that, not degrees. Now, that solution that I showed you is really, really nasty. And it's not very fun to calculate in your calculator, especially on one of my exams. And so a really smart engineer said, you know what, why don't we just pre-solve those solutions and plot them graphically using a term where we make a ratio or a normalized induced stress. It's normalized by the load that we placed on the soil in the first place. So if I just take that ratio, solve that equation, and solve for this ratio, we're going to call this ratio I. That's what I call my influence factor. And remember, that influence factor is simply the solution of those equations that we showed you over here. Okay, where there's Q, and this whole thing here, that is I. Got it? Good. Okay, there's the I. So now, if we plot this thing, what we tend to see is if I just take half of my footing, or my strip load, and then I flip it up on its side, so now I'm looking at the side of it, and I'm looking at the cross-section of the soil beneath it. I is plotted in terms of it's a ratio, anywhere between 0, that's way down deep, all the way up to 90% at this depth of about, this normalized depth of, what would that be? Each one of these is 1B. Oh, that's 0B right there. So that would be a depth of maybe 0.25 times the width of my strip footing. That's where I have 90%. If I'm directly beneath my footing right here, I is going to equal 1 because it's going to feel the full weight or the full load of that strip load. These solutions are really, really nice, and we call them isobars. They represent a graphical solution to the Boussinesq equations that allow us to physically see and try to understand what the stress distributions look like. So think again of these influence factors, as contours, or these isobars as contour lines of induced stresses. And you kind of see how beneath the load, it makes like a bulb shape. So sometimes we call these things a stress bulb. Now, you'll notice in this particular plot that at a depth of 5 times the width of my footing, that I, right at that level, is about equal to 13%, or 0.13. And think about that, right? Say I have like an 8-foot wide strip footing. That means that at a depth of 5 times 8, or 35 feet below the ground surface, the soil is still feeling 13% of the load that I applied at the ground surface. So the question is, how deep do we need to go to worry about the soil but still remain practical? Because according to elastic solutions, if I go down to a depth of infinity, I'm still going to have some I value. It may be really, really, really small at a depth of infinity, but there's still going to be a non-zero value. So the question is, how deep do we go but still remain practical? Well, that really depends. It depends on the importance of the project and really what the consequences are going to be of being wrong. So we call the zone that we're worried about, or the zone of the stress bulb that we're worried about, we call it the zone of significant stress. And that's an important term for me, and I want you to become familiar with it and know what it means. The zone of significant stress is the zone beneath our load that we're worried about. Anything that's outside that zone, we don't care about. We're going to assume that it's not going to have a significant impact on the soil. So generally, geotechnical engineers assign the zone of significant stress as anywhere where our induced vertical stress is going to be between 20% to 10% of our applied load on the ground surface. So in this particular plot, it would be anywhere in this vicinity that I'm coloring. If that was a more critical project, to anywhere in this vicinity of 20%. If the project was maybe less critical. And you see, man, that's a big difference. Look at all that soil there, which would mean that if I was assuming 10%, in influence factor of 10% for my zone of critical or significant stress, I would have to put my borings deeper into the ground to characterize all of this soil down here, which costs more money. That's less money in my pocket. So really, in terms of a strip load, the zone of significant stress is going to be anywhere between depths less than 3B to 7B below the bottom of our footing. So let's do an example of a strip load calculation. Let's say I have a strip load that's 10 feet wide and that has a uniform stress of 2,000 pounds per square foot that I'm applying to it. I have a 3-layer soil system of silt, clay, and soft clay, each one 10 feet thick. And I'm interested in computing the stresses at a point in the middle of each layer, point 1, 2, and 3. And those points, by the way, happen to line up directly with the center of my footing. For this example, that's just the way they are. Is there anything wrong? What if I had said I want them out here outside the center of my footing, maybe even outside the footprint of my footing? Yeah, I could have done that too. but for this example, we're just beneath the center of my footing. Okay? So here's what we need to do. First, we need to compute the initial effective stress. From our previous lessons, we learned that this is what we call the geostatic stress. So the effective stress at point number 1 is simply going to equal 116 pounds per cubic foot times the depth, which would be 5 feet. So I get 580 pounds per square feet. Notice, by the way, that the water table is at a depth of 10 feet, which means that below that depth of 10 feet, total stress is going to be different than effective stress. But above the water table, we're going to assume that total stress equals effective stress. Okay, at point number 2, we have our stress from point number 1. So we need to add to it some additional stress. Let's add to it the stress from this layer of soil, which will be the 116 pounds per cubic foot times 5 feet of thickness. And now we need to add to it the effective stress from this portion of the soil, which will simply be the buoyant unit weight of 120 pounds per cubic foot saturated unit weight minus the 62.4, which is the unit weight of water. So that's going to give me 57.6 pounds per cubic feet times the thickness of that soil, 5 feet. So that's going to give me 1448 pounds per square foot. Now, take a stab at point number 3 on your own, and so pause the lesson, and then we'll come back and calculate it together to see if you got the right answer of the 1944. Go. Okay, hopefully you're back and you were able to obtain the answer of 1944 pounds per square feet. If you didn't, if you are confused on how we calculated these numbers, please come and get help. Get it from a TA or come and talk to me, because it's important that you be able to compute effective stresses in the soil. To get the effective stress at point 3, we'll start with our effective stress from point 2, the 1448. We'll add to it the stress from the remainder of our stiff clay layer, which would be the buoyant unit weight of 57.6 pounds per cubic foot times the thickness of that remaining of the layer, which is 5 feet. And then we need to add the stress of the top part of the soft clay layer. Its buoyant unit weight is 42.6 pounds per cubic feet, and it has a thickness again of 5 feet. So when I do that, I get the 1944 pounds per square foot. Okay, so that's step A. Now that I have the effective stresses prior to the load, again, those are the geostatic stresses, I want to compute what the induced stresses are from my strip footing. So in order to do that, I'm going to use the Boussinesq solutions for a strip footing. I'm going to use this isobar chart right here. So in order to do this, I need to compute the ratio z divided by b for every single one of my points, point 1, point 2, and point 3. So point 1, my depth is 5 feet below my applied load. Remember, z is going to be the depth below my applied load. So I'm at a depth of 5 feet. For point number 2, z is going to be a depth of 10 feet plus 5 feet. So that's going to be 15 feet. For point number 3, z is going to equal 25 feet below my applied load. B is always going to be 10 feet because remember, B is the width of my applied load or my strip footing. So once I get these ratios, I get 0.5 for point number 1, 1.5 for point number 2, and 2.5 for point number 3. Why I'm computing these values here, because these values are going to be the depths on my isobar chart. So now I'm just going to go to my isobar chart. And because I'm directly beneath the center of the footing, I'm going to be drawing my points directly beneath the center of this applied footing. Now you may wonder, why don't they draw the rest of this thing? Well, the reason for that is because it's symmetrical. They don't really need to do that. It would just be a waste of space and a waste of paper. So here we go. If I'm at a depth of, for my point number 1, I'm at a value of 0.5b right here, and I'm directly beneath the center of my footing. So that's where my point goes. And I interpret my I value, which is going to be approximately 0.77. I is going to equal 0.77 for point number 1. Okay, for point number 2, I'm going to be at a depth of 1.5b, and I'm directly beneath the center of my footing again, and that's going to give me an I, or an influence factor of 0.39 right there. For point number 3, I'm at a value of 2.5 times my footing width below, and directly beneath the center of my load again. Whoops, I'm not sure why that zoomed in. That was strange. Okay, when I do that, I get and interpolate an influence factor of about 0.26. And again, I'm just interpreting these, or interpolating these from these influence factors that are plotted on the isobar chart. So now it's just a simple calculation, folks. All I need to do is multiply that influence factor, because remember, delta PZ is simply influence factor times my initial load. Computer's being finicky today. So influence factor times initial load. I times Q, I do that for all of my points, and that gives me all of these values right here for each of those 3 points. Now I want to pause and let's review what these points mean. Again, these are the stresses, the additional stresses that the soil is feeling due to my placing a strip footing on the soil. These do not represent the stresses that the soil was feeling before the strip footing was placed. Those we computed in the previous step. Okay, for step number C, all we want to do now is compute the total effective stress, or the combined effective stress that the soil will be feeling after I place my load. So all I have to do is add my initial effective stresses, or my geostatic stresses, to my induced stresses. And when I add those together, these final stresses are going to be the stresses that I'm predicting the soil will be feeling after I place my strip footing on the ground. Hopefully you see how this approach and how these procedures can be very useful and powerful for geotechnical engineers to allow us how a soil element might feel stresses from when we apply different types of linear, point, and strip applied loads, or induced loads. So that's it for today's lesson, and be sure to tune in next time. We're going to continue with this topic, but we're going to be talking about area loads with the Boussinesq solution. So have a wonderful day, and I will see you next time.